Hello, everybody. The semester is winding down, right? So we have today's lecture. We have 2 more lectures next week. Then I will be gone for a week, which gives you a whole week to work on your projects and on the assignment. And after that, we will do project presentations. So what I will do is probably just take the list of students and assign students randomly, well, probably alphabetically, to the 2 lectures at the end of April. For now, I will assign individual students. I know that some of you want to work together. I know you want to work together. Could you just shoot me an email and let me know who will present together so that we can organize it? It's still a bit off, but just to give you a heads up that this will be coming. Okay? So let's get going today. I want to go back to distributed computing today after our hiatus into GPU programming. We had the last 2 lectures. And that distributed parallelism will stick with us for the rest of the year. I really want to introduce things a bit more thoroughly, give some examples, show you some ways to implement distributed parallelism in the real world and how to write applications using that are distributed across several nodes and utilize the full power of those machines. And as always, I will focus on HPX to do that. Today's lecture, and we might not be able to do everything today, depending on time, how time will permit to do that. But I want to do some recap of the single program multiple data programming model and the CSP model, which is the collective sequential processes, communicating sequential processes model. Just to put you back in the mindset, because it has been 2 weeks, I think, since we last talked about it when I introduced it. And there has been that GPU programming in between, there has been the spring break in between. So I want to kind of get us back into the mindset of that. I want to introduce or give you a hint how you can reason about these distributed applications based on a very simple mental model, which is important. Because in my experience, when you come from programming against a single machine, like your laptop or your desktop, it's quite a stretch to rethink how to approach programming, how to approach writing these programs. So having a mental model that helps you and guides you while doing that is I think, very, very useful. I want to introduce 2 very simple, what I call 4-function HPX codes. One that will focus on point-to-point communication, so where 2 localities communicate with each other exclusively. And the other one is about collective communication, where many localities, many nodes participate at the same time in that communication operation. And most likely next time I will start to actually looking into real Laplacian code, Laplacian equation solution. We already touched on that a bit from the theoretical side, but this time I really want to distribute that across the machine and create some stencil code that works in distributed. Okay, so where are we? I talked about Amdahl's law. I hope everybody remembers Amdahl's law, which is that theoretical consideration Amdahl came up with that gives us a theoretical limit of how much scalability we can achieve in an application when we add more cores to it. And as Amdahl has derived a very simple mathematical model that tells us that the speed up I can achieve by adding more cores to an application depends on the amount of parallel code I have in my application relatively to the whole thing. So just to remind you, if I have parallelized 80% of my application, I can achieve maximum a factor of 5 in speed up. And that doesn't matter how many cores I actually throw at the system. Theoretically, it's not possible to be faster than 5 times. If I parallelize 99% of my application, which is almost infeasible, I can theoretically achieve 100 times speed up and not more. Luckily, we discussed also that there is a different approach to things that doesn't rely on just taking the same problem and throwing more compute resources at it, but an approach where instead of just adding more cores, I also increase the size of the problem. So when I double the size of the problem, I double the number of cores. When I improve or increase the size of my problem by a factor of 10, I run it on 10 times more compute resources. And if you look at this model of scalability, which is, by the way, called weak scaling, we see that we actually can linearly improve our performance and linearly scale up in terms of amount of computation we can do. And this insight has led to further considerations where we said, okay, we have that distributed memory system, we have several nodes interconnected with a high-speed network. And what about if we increase the data size more and more and more? And if the data size is getting too large for a single node, we start distributing that amount of data across several nodes. But then we immediately ran into the issue that we said, okay, we can do that, and we can run a program here, and we can run a program here. But somehow we have to distribute the data because each of those nodes has its own address space. And there's no way for a node B to access data that is stored in the memory of node A directly. So this doesn't work. And this is kind of the dilemma we're in. We have to find a programming model that allows us to overcome that, well, not overcome, but to deal with the situation that each of those nodes has its own address space. And there's no direct way for code that runs on this processor to directly access a memory that is connected to the other processor. We have to somehow go through that interconnect. And that requires us to come up with a scheme of programming things that is actually manageable, right? So that we can still reason about the problem and that we can design code that works under these circumstances. So even if we have that situation that we kind of split things, right, and that we have more data than we can actually store on a single node, we have a couple of more questions that we need to answer. Well, first question is, should all those nodes should they do the same thing? Will we get speed up if they do exactly the same thing? Will that work? If we add more CPUs, we can make the problem bigger, right? Gustafson's law tells us that this at least theoretically should lead to more scalability. But can we keep all the data in a single node when we make the problem bigger? Well, obviously, there's a limit to it, right? We have a certain amount of memory available in each of the nodes. And when we start adding more and more data, make the matrices even larger and larger and larger, they will not fit into the main memory of a single node anymore. So it's not possible to keep all the data on all the nodes. Do we need to keep all the data on all the nodes? Well, probably not. We should find a way to divide the data into pieces and assign these pieces somehow to each of the nodes, so that node 1 cares about one half of the matrix and the other node cares about the other half of the matrix. And last but not least, we have to decide what do we keep, right? Which of the data do we need on each of the nodes in order to still orchestrate our algorithms, the stuff we want to implement. So in the end, what people have come up with is a, well, probably very straightforward answer by saying, let's split the data in a way across and distribute it across the nodes in a way that collectively all the data is somehow represented. There might be overlaps between the pieces of data if needed, but it has to be collectively exhaustive. I have to somehow store all the information I need for my application. Sounds kind of trivial when I say it, but this is a fundamental insight that is a basis for how distributed applications are being orchestrated. So, okay, for the data we have decided we know how to do that, right? We just split things into pieces and distribute it across the system, make sure that we don't lose any data by doing that, and that's it. If we need more data, we can always create smaller pieces and distribute it across a larger amount of nodes. What about the program? Does it grow with the problem size? Is the code larger when I just add more data? Well, probably not. Right? The array dimensions are usually runtime parameters anyway, so I just use a larger number for my array dimensions in the end. So the program itself, the code, does not change or does not grow with the problem size. It might get a bit more complicated when I want to do distributed computing, but it is not proportionally growing with the problem size, which is the important part. But on the other hand, we probably need all the code everywhere, right? If you have a piece of data, the amount of code needed to work on that data probably doesn't depend too much on the size or on the amount of data I have. So I need all the functionality I encoded in my program on all the nodes, and which leads to exactly what we discussed, to that SPMD programming model, where we have a single program that has all the code in it, which is running on all the nodes, and is the same on all the nodes. And we have the multiple data part, where the data is split into smaller pieces, so the data is not the same on all the nodes, but it's collectively exhaustive. So the sum of all the data on all the nodes is comprising the overall problem. Then we discussed Huare's theoretical findings, where he developed a theoretical axiomatic system that allows us to reason about or to prove that this is actually a feasible approach, where he called it Communicating Sequential Processes. Well, don't be fooled by the word sequential. That I think it's an artifact of the time when he came up with that model, because at that time we didn't have to deal with multi-core systems in the first place. Nowadays, it's probably communicating parallel processes, especially when you're dealing with HPX, where you have parallelism on the local node and you can still distribute things in addition. But let's stick with the term of communicating sequential processes as the kind of conceptual model of that, where every node runs a sequential process, well, nowadays locally parallelized, and all of the code is replicated across all the nodes. On the other hand, the data is distributed using some resource allocation mechanism. You somehow decide how to distribute the data. The problem is that the data dependencies are probably not disjoint. And we discussed that, right? When you have, for instance, a simulation of a galaxy with 1 billion of stars you want to simulate, and you want to follow the movement of each of those billions of stars. So if you find a distribution scheme for these billions of stars, where you say, okay, I divide my number of stars into equally sized pieces depending on how many nodes I want to run it on, then each of the nodes is responsible for one of the stars in the overall galaxy. But what happens when one star actually moves over to another, to a region of responsibility of another node? Or how do you compute the forces between two stars when one of the stars is on one node and the other star is, the responsibility for the other star is actually on the other node? So the data dependencies between those entities in your program are not disjoint. You can't split them up in an easy way. So that will require additional thinking. Data may be needed by another node, but can't be accessed directly. Well, this is part of this cross-node data dependencies. But again, the union of all partitions is the whole program. And this is a fundamental way all of these distributed programs are written today. And I want to focus on that today a bit more and show you how can we implement that? How can we take that mental model, which is described here, and cast it in code in a way that we still can reason about all of that. Okay, so in summary, every process has its own memory space, has its own node it works on, it runs on. It's a normal Linux system with a normal Linux process, and that Linux process just works with its own memory and is constrained to work with its own memory. We have several nodes. All of those nodes run the same code in their own processes. So each of those nodes has its own operating system. And when I launch that collective set of processes, each of those nodes launches a copy of that code as its own process. Then we partition the data, and the partition data is the whole program, as we said. Just to go back to our example, we introduced that integration and calculation of pi. The problem we have discussed many times now, so I'm not going to be very detailed about that. But just to remind you what we came up with when we talked about it last time. The idea was that I want to calculate the integral, so the area below that curve, which gives me the integral I'm looking for, which in that particular case would be the number pi. And I approximate that by creating these rectangles, and the assumption is that when h goes to 0, so when the width of those rectangles go towards 0, the result we are achieving gets more and more correct, more and more closer and closer to the actual value of pi. So the sequential program we started off with is shown here. It's a simple loop where we compute the area of each of those rectangles and sum it up, which in the end will give us our approximation of pi we're looking for. When we distribute that across a system where we have several nodes, those nodes are interconnected with a high-speed network, we said, okay, how would our program look like if we did that? And as you can see, the code itself is still there, right? The code that is doing the actual computation is still in place in the very same way as before. Essentially, it's a one-on-one copy of what we had before. The only difference is that now the iteration boundaries are not 0 and the number of rectangles, but each of those nodes has its own begin and end range for the iteration, and that begin and end on the different nodes is computed in a way that each of the nodes is responsible for a certain subset of the rectangles of my integral, and but we make sure that we don't lose any rectangles. So collectively exhaustive. That requires us to do additional computations, so we have to somehow compute the begin and end of our iteration, which is different on each of those instances of the processes, and we compute it based on two values: A, on the knowledge how many of those processes are connected to it, how many of nodes are involved, and what is the sequence number of each of those nodes. And once we have these two numbers, which we in this case ask HPX, the current process, and the current process can give you that information. One function get num localities, which gives us a number of connected processes in that collective application. And the other one is called get locality ID, which gives us a sequence number from 0 to n-1, representing a unique number of each of those processes, which allows us to do the computation of the begin and end iteration separately on each of the localities. Great. So we got to a point where we have exactly the same code running on 4 times, but with different parameters, and we choose those parameters in a way that we get that collectively exhaustive set of data we are interested in. Good first step. So what is missing? If you look here at the code, it misses some things. It assumes that the n is the same on all of the localities, on all of the processes. And for now, and even this code just looks at the command line argument only on locality 0. So it will not work the way it is shown here. What we need to do, we have to ensure that all the processes work with the same n. Otherwise, we don't get that collectively exhaustive set of data. The other thing is that for now, each of the localities collects its own partial pi result. So we have to find a way to sum up all the pi's on the 4 processes and then print the result on locality 0. So how do we do that? The way we do that is by using so-called collective operations, where we assume that process 0 receives the n from the command line. So the user passes n on the command line, and somehow that n has to be distributed to all the other processes. So process 0 sends that n to all others, communicates that with all others, and this operation is called broadcast. And the way we do that in HPX, there's a function which is called HPX collectives broadcast. We give it a first argument, which is a communicator. I will talk about communicators in a minute. And we pass n there. And after that operation is finished, all localities have the same value of n stored in that variable n. And we will see in a moment how that works. Okay? Then we do the calculation on its own. We calculate begin and end on each of the processes based on the locality of that process and that n that was received. Then we can do the computation itself, the subintegral for the range that particular node is responsible for. And in the end, we somehow have to sum up all the partial results. We have to do a reduction operation. We have to send all the partial results to locality 0, and locality 0 will sum them up and will print the result. And in HPX, that is called collectives reduce, because it's a reduction operation. Again, on the world communicator, I'll say a word about that in a minute. And I'm passing my local version, my local value of pi to it. And that will magically make sure that that locality 0 will come out with a pi which has the sum of all the partial results. Exactly what we need. Okay, so let's look at the code as a whole. We have still our sequential execution here. So this is what we started with, these 3 lines. We have the computation of our loop boundaries as before. What we added here is 2 things. The broadcast operation, which is invoked before the actual computation happens, but after the locality 0 has received its value from the command line. And once everybody is done, there's a reduction operation which will make pi appear to be the sum of all the sub-partial results sent by all the localities, and locality 0 will print them. So we have several parts now to our distributed application that is the following. First, we have to figure out what is our locality ID, what is our sequence number in the currently running set of processes, and how many processes are connected to that application in the first place. Then we get n from the command line and share it using the broadcast operation with everybody else. Then we do our own computation on each of the localities, now based on the sequence number, the number of localities, and that particular value n. And in the end, we do the reduction operation, where locality 0 collects all the partial results and adds them up and prints them. The reason why I'm so exhaustively explain that is that this is a pattern that is ubiquitously used in all distributed applications. So whatever distributed application you look at, you will always see this kind of scheme. You always have these 4 steps somehow encoded in the application. First, figure out what process I am, then distribute all the parameters everybody needs to do the computation, then do the actual computation, and then collect the results and bring them back to one of the localities and write them to a file, write them to the console or whatever. So this is what Andrew Lumsdaine calls distinguished replicated processes with distributed data, or DROP-D. And this is a scheme you can apply to any problem. When you start off with a sequential problem, which works on your laptop, you can apply this scheme of transformation to it, and you get very quickly to the point that you have a distributed application. What might change between applications is what you actually broadcast to the others. What will probably change is what do you actually collect in the end in terms of results. The actual computation is probably different as well, but the general underlying scheme is absolutely the same. So whenever you're in doubt how to write a distributed application, copy this slide, copy the code, and replace the parts of it with whatever your application is actually requiring. And that will solve the issue. So there's a very straightforward thing to get from a from a sequential application to a distributed one. Yes?
Does the reduction occur at all localities?
Does the reduction what?
Occur at all localities.
Well, this code is run on all localities, right? We distribute the code and make sure that all localities run the same code. So broadcast is called on all localities, just that it will do different things on different localities. On locality 0, it will take the n, and on other localities, it will put the received value into n. The reduction is the other way around. You call it on all localities, everybody supplies pi, but only on locality 0, pi will be changed to be the sum of all the collective pi's. So the magic is happening inside broadcast and inside reduce, so that you get a scheme which is fairly straightforward to work with, and you don't have to worry about these things. Okay, make sense? Other questions about that? Okay, cool. So to summarize, we have the situation that every of these processes can only read and write to its own memory because it works on a normal computer. One process sends the data, other processes receive the data. So these processes operate purely local. That is important to understand. There's no reaching out into the memory space of another node. Every of these processes runs completely locally on the node where it's running. So every process talks only to its own memory and to its own networking devices. Again, there's no magic reaching out to another piece of hardware which is just on the other end of the system. We say that it is as if we were working on a shared memory, but everything is local. So this as if is kind of a central understanding, central notion of what's happening. We create the illusion as if everything was shared, but it isn't. And that illusion is being created by these collective operations and by the way we write that code. So as strange as it may sound is that a parallel program doesn't actually run parallel, even if it's locally parallelized. Okay? It doesn't run in parallel in the sense that a processor can't access the memory of another node, but it runs in parallel in the sense that you have several processes that run at the same time, concurrently, on different nodes, and that each of those processes can be internally parallelized by using parallel for loops or threading or all the techniques we have been talking about. Nothing prevents us from doing that. But this is purely for the computational part of the partial result where I apply local parallelization. And everything else is somehow organized using these collective operations. So we are running multiple copies of a sequential program. Well, nowadays that sequential program, as I said, is probably parallelized locally. But all copies execute exactly the same code, even if that's not happening in lockstep. The only lockstep that might there be is that the collective operations have to wait for everybody to invoke them before everybody can proceed. But in between those collective operations, there's no lockstepping, there's no synchronization in between processes. The synchronization really happens only at the points of collective operations when data is being exchanged. And in those points, all localities have to call the collective operation in order for all the localities to make progress. So if one of them doesn't call it, everybody else will wait for that thing to happen, which is the other thing to keep in mind. Okay, so let's go back to HPX. And a very simple HPX program I wanted to kind of recap and remind you of is this. We have a normal main, and we have to include two additional header files. One which makes all of HPX available, it's that HPX header, and another one, the HPX main one, which is needed only in the file where you actually have a main function. And this HPX main will make sure that HPX will be initialized when main starts running, which is the most convenient way to use HPX. So you don't have to worry about initializing it or how to tear it down. All of that is magically happening in that HPX main header file. Then we call getNum localities, which gives us a number of connected localities. We call the getLocality ID, which gives us our sequence number between 0 and num localities -1. And then we print the result. Very simple. Right, in this case, I'm just printing the localities IDs and the number of connected localities. What can we do with that? Well, we can use a very simple CMake build system. C++ has a bad reputation that it's very difficult to set up a system that depends on other things. When you want to write an application, you have to kind of do complicated installation of all the dependencies of that application. This has been improved recently quite a bit. And as you can see, in the end, to make that happen, at least for HPX, all you have to do that find package in CMake, which finds HPX on the local system. So you have to have it somewhere pre-installed. Then you tell it, hey, please create one executable, which should be named Hello World, which has to be built from this CPP file, which I specify, and you can specify many CPP files if you want to link them. And then you additionally tell it, and by the way, my Hello World depends on HPX itself. That's it. It will build the application. The additional thing I added here is an artifact of HPX, which is really an historical artifact. By default, if you run an HPX application and distribute it, by default, it will launch main only on locality 0. On all other localities, main will not be called, which is a bit confusing, a bit weird, but that's the way it is. In order to circumvent that from happening and to make sure that main actually runs on all the localities, not just locality 0, you have to add that preprocessor constant to the compilation, which is have run main everywhere. And that will make sure that your application, when you launch it, will actually execute main on all localities, which is exactly what we want, right? Because otherwise we will not have that illusion of that everybody's doing the same thing. If one of the nodes calls main, the others don't, then this is kind of broken. So that's why when you do these drop-D style applications, always define that preprocessor constant in your build system, and then everything is fine, and main will be invoked on all of them. How do I run more than one application on a cluster? Well, I don't want to type the name of Hello World 5 times or 10 times in 10 different terminals to launch it on 10 different nodes in the system. You don't want to do that. So HPX comes with a utility which is called HPX run. It's a Python script. And that Python script can launch things with a given number of localities. So you could say HPX run -- localities equals 4, and then run Hello World. And that will run Hello World on 4 times. And as you can see, the sequence number will change for each of those localities because they are connected. And everybody of them will know that there are actually 4 connected localities to it. So you can launch these distributed applications by a single command line. Very convenient. It has more options, so you can do --help for a list for more options how you can use HPX run, but this is outside of the scope of what I want to talk about. So we now know how to build an HPX application, how to make sure that every node actually executes its main function, and how to run it on the target machine in a way that I still get exactly what I expected, namely my hello world 4 times on 4 different from 4 different processes. So this has launched 4 processes. In this case, the processes were launched locally on the same node. So you can do that as well. But you see the processes are aware of each other, right? Otherwise they wouldn't know that there are overall 4 and they wouldn't get the appropriate locality ID, unique sequence number of those processes otherwise. By the way, it's pure coincidence that the number is just increasing here. So it could come in any sequence, obviously. Okay. So let's get back to the notion of that communicator I mentioned when I introduced these, or when I talked about the collective operations. So these communicators represent a set of localities. And when I use the communicators and the collective operations, the other question I have to answer is, what is it what we're actually sending, right? We pass n to the broadcast. Is n sent over to the other localities? What is it? What is being sent? Well, what's actually being sent is a value of n, and not n itself, because n is a variable that only the compiler has knowledge about. So actually code doesn't know anything that the variable is called n. So because n has meaning only in source code, so the collective operations will send the value of n. And what does it mean to send the value of an integer over the network? Well, you send the bits that represent that integer. What does it mean if you send a vector of doubles over the wire, over the network? Well, you send a bit stream representation of your vector of doubles that somehow turns a C++ object into a bit stream, and on the receiving end, when that bit stream comes in, there's a way to reconstruct the standard vector of doubles from that bit stream and have the same value as I had on the sender. And that is important because we want to create that as if illusion, as if these things were the same, even if they are copies that are distributed across the processes. So we are sending the bits that are somehow representing these data types. The other question is, where do we send those bits? How do we say send it to another process, or send it to n in another process? Because n again has meaning only in source code, and its location of the variable in process 0, the address of n in process 0 could be different from the address of n in process 1. Nowadays, when the operating system loads executables, it randomizes the base address of these executables. So each of the nodes will probably have a different address of n. So how do I put it in the right place on the receiving end? But there are ways to make that happen, because both ends have compiled the same code. So each process on its own knows where its n is. And we use that facility and that information to actually be able to place things in the right place. I want to kind of take a step aside and talk a bit more about that process of turning things into bit streams and turning it back into objects, which is called serialization. What HPX does, it allows you to send arbitrary variables of arbitrary C++ types. So you can have any type you have in your application, and you can pass it to broadcast, or you can pass it to reduce, or you can pass it to any of the other collective operations. And HPX will make sure that a corresponding bit stream representation of that particular object, of that particular type you have, is created underneath the surface, is sent over the wire, and on the receiving end we are able to take that byte stream and recreate exactly what we had on the sender. So there are two terms we use. Serialization is the process of converting a C++ object into a byte stream. And well, deserialization is the opposite. You take a byte stream and you turn it back into a C++ object of a known type. So you have to know what type to expect on the wire, because the byte stream itself doesn't encode what type it represents. It's just a set of bits. So in order to do serialization, the receiver and the sender have to agree on the type that is being used. When you send an integer, you better expect an integer on the other end. If you send a double, you better expect a double. Otherwise, we talked about types in the very beginning, right? So types are the rules how to interpret bits. And if you don't have the types, you don't know how to interpret the bits. That's why serialization, and especially deserialization, is very much tied to the type of the C++ object. So once we have serialized things, HPX sends the byte stream generated from the arguments of broadcast or of reduce or of anything else over the network. And by the way, the return values are handled the same way. So some collective operations have return values. So the return value gets back and is serialized and deserialized in the same way. Now you might ask, how does HPX know how to serialize arbitrary types? I come up with my own types. How can it magically figure out how that should be serialized? Well, the idea is the following. All pre-built-in data types are supported out of the box. So integers, shorts, longs, doubles, floats, you name it. All these types are supported by serialization without you having to do anything. All container types are supported. So if you want to send a standard vector of something, then you can do that as long as that something itself is serializable. So you can send a standard vector of a standard vector of a standard vector of integers, and that will work out of the box. It supports many other types from the standard library. I just named a couple. Tuple is probably the most interesting one in our context. But any type the standard library exposes is supported, and you don't have to do anything about that. And we support many of our own types, like futures. So you can send a future over the wire. You can just pass a future to broadcast if you want, and it will come out on the other end as a future, and you can do things as normal. What about those types that are not known, that your own types, you want to serialize them, you want to create a point that represents the coordinates of something and has a vector of doubles stored in it that represents the data for this particular point. And you want to use reduce, or you want to use broadcast to communicate this type. Well, the easiest way, it's a very simple thing. All you have to do is you add an additional function to your type, which has to have this prototype. It has to take a first argument, which is called an archive, as a template argument. And the second argument is not used. You can ignore that. And inside that function, by the way, the name has to be serialized. And inside the function, you use the archive, which comes as the first argument, and you list all the members you want to serialize just using the ampersand. Might sound strange, but in this context, the ampersand can be read as, please serialize that if called on the sender, and please deserialize it if called on the receiver. So that ampersand has different meanings depending on what archive is being passed in. If the sending archive is passed in, this means turn it into a bit stream and store the bit stream inside the archive. And if it's called with a receiving archive, then it takes the bit stream out of the archive and puts it in place for the variables. In other words, you can create serialization for arbitrary types easily. So if you have your special things you want to send back and forth, well, here you go. Just add that one function, copy paste it, and add the list of things that are part or that you need to send and recreate, just delimited by ampersands in that function, and that's it. And that will enable serialization for that and will allow you to send this point or instances of that point or vectors of points or whatever you have over the wire without additional need. Any questions about that? So again, the important piece here is to understand that we can't send n over the wire. All we can do, because what is the network? The network is an electrical wire where we put the bits sequentially on it. Right? It can send bits and not bytes. It's a single wire where the bits have somehow to go over as electrical signals. So we have to turn what we want to send, the C++ object, the thing that is interesting to us, we have to turn that into a sequence of bits, low-level bits, up and downs, zeros and ones. And those zeros and ones go over the wire, and on the other hand, the network card turns that back into bytes, and then we can use those bytes to turn them back into a type by knowing what is the type of that has to be recreated on the other hand. And that's why it's so important to call these functions on all localities, because on all localities we pass pi to the reduce function, and that means that helps us to identify what type to expect, right? The locality 0 passes pi as well, which is a double, which allows us to know that actually at this point a double is expected to be received, so we can recreate the byte stream into the right type. Okay. So far, just as a side note about serialization. So let's get back to that mental model I mentioned in the beginning. So you can think of that the HPX communication takes place in the context of a source locality and a target locality, or several target localities, where each of those localities is exposed by one of those sequential processes. And we have the sequence number of them, right? We expose two types of communicators in HPX. One for peer-to-peer communication, where you want to send things from one locality to a dedicated other one, which we call channel-based communicator. And the collective communicators like broadcast and reduce, we use when several localities have to participate in a particular data exchange with certain semantics. We have two predefined communicators, and that's the two ones. I've already been using the collectives get world communicator, but there's an equivalent one for a channel communicator. And these two predefined communicators represent all the connected localities. So all of them are somehow represented by an object that is returned from the world communicator. So when I use the world communicator on a collective operation, that means that all localities have to participate in that collective operation. I can constrain it to just a subset if I want by creating another communicator, but in our case we probably will use only the world communicators anyway. So let's talk about these communicators a bit more and understand what they actually do. A channel-based communicator enables the peer-to-peer communication between all localities that are part of the communicator. So if I have the world channel communicator, it encompasses all localities, and that means that each of the localities, each pair of localities that are part of it can communicate in a peer-to-peer direct fashion using that communicator. So a communicator is in a sense a list of localities with its associated process ID. It represents the set of possible endpoints and possible processes that will be able or have to participate in a certain communication operation. If the channel-based communicator enables peer-to-peer communication, the other communicator for collective operations groups several localities identifies several localities and defines which of the localities have to participate in a collective operation that is where this communicator is used. So only localities in the communicator can use it, obviously. All processes in the communicators see an identical list of localities. So again, the behavior is as if this list was global. So it's the same list of localities that is identified by a particular communicator, and everybody sees the same list. The index I was talking about, the locality index, is actually the index of the process inside a communicator. I was just using the global functions because the global communicators have the same indices associated with them as the index number of a locality in a particular communicator. So you can think of the index as a sequence number of a participating endpoint. The size of a communicator is defined as a number of endpoints, and the endpoints can query for the size and for their own index in the communicator. So when I use getWorldCommunicator, I can ask it, hey, what's my index number inside this particular communicator? Or how many communicators do I have in there? So another way of finding out what is the number of localities and what is the locality ID of the running locality is just to take the world communicator and ask it for its information. It's probably an easier way to do that and more portable. So this will do almost the same as the examples I had before, where I was calling the HPX getNum localities and so on. Here I'm asking the communicator, how many localities are connected to it, and what is my index inside that communicator. The same can be done for the channel communicator. So you can get the global world channel communicator, you can call getInfo in it, and it will give you the same information back, but this time pertaining to the channel communicator. Not much unexpected, I think. It's really just a way of dealing with the set of localities that are connected to a particular operation. Okay, so instead of calling the other two functions, I'm now using the getWorld communicator, and I use getInfo to extract the two pieces of information I need, namely the num localities and the index ID of my locality. Then again, I do the same broadcast, and as you can see, I use the same communicator with the broadcast operation. Then I do my integral, and then I do my reduction as before. Same code as before, but this time tied to the communicator, the set of localities that are connected to the overall application. That's why it's called World Communicator. Everybody is part of it. And as I said, you can define your own communicators where you say only this, and this locality is part of it, and then do the same broadcast operation, but in that case, only these three localities will participate in it. But in the general case, I think most of the time you will probably use everybody. You will not partition your application into different communication regions and things like that. But it's possible if you want to. Just a word about what is a channel and why is that thing called a channel communicator. Well, you can think of a channel of being an abstraction of a peer-to-peer communication operation. So essentially, you're calling your friend. Right, over the wire, over the phone, you communicate with your friend only. And this is, in some sense, a communication channel. So the channels that are represented by the channel communicator are nothing else. It's really dedicated connections that you can use to send data from one of the localities to any of the other localities that are part of that communicator. And the interesting thing is that the channels are asynchronous. Asynchronous in the sense that it has two ends. There's a get function and a set function. So set puts data into the communicator, into the channel, and get gets the data out of the channel, where the sequence of values that come out using get is the same as a sequence of how you put things in. So when you put in 1, 2, 3, 4, call set 3 times, then the get function will receive it in the same sequence as you have put it in. So it's a pipeline if you want. And the send and receive operations can be asynchronous. That means that send and receive both can return a future. So you can use the communication operation and make it asynchronous. You can say, okay, send this and give me a future and tell me whenever you have accepted the data. Or you can call get on the channel and say, hey, please become ready whenever data comes in. So you can decouple things from each other by using these futures we talked about. So it's a unidirectional pipeline between two endpoints. The channel can hold one element at a time or many elements at a time. It really depends on the implementation. You create a channel on one locality, send it over the wire, and you can use it on the other end as on the receiving end. When you use the channel communicator, you don't have to send the channel over, right? The channel communicator is just creating a bunch of channels that connect all of them. So it's a higher level construct. So the channel communicator is a collection of channels, one for each combination of endpoints that are listed in it. And as I said, they are asynchronous in nature. Channels expose two functions, get and set. Both return futures, but we have synchronous variations, and we will show how those work in a minute. Okay, so just give you a sense of how do these functions look like. When you use a channel communicator, there is set. You pass it the communicator that should be used for the communication. You tell it where to send the data to, which is that site argument. You tell it what value to send over the wire, what type. So T is a template, so you can send any object in C++. And the tag is an additional argument that allows you to identify that particular communication, because you can have several connections between two localities, and the tag uniquely identifies each of those communications. So it's kind of an identifier for a particular communication operation. You can leave that off. By default, it's 0. So in the simplest case, you might not need a tag. Obviously, the sender is implicit, right? The receiver is explicitly specified, and the sender is implicit by the locality that is calling set. So you don't have to specify where does the data come from, because you're calling set on a particular locality. This is the synchronous version, where you have to pass an additional first argument, which tells it to be synchronous. But if you leave that off, then you get an asynchronous version, which gives you a future, as I said, and that future will become ready whenever the whenever the channel has accepted your value. It will return right away, but it will give you a future, and that future will become ready sometimes later when the channel has received the value. The opposite side is get. Again, the synchronous version needs that additional argument. Otherwise, the arguments are the same, except that now the side argument represents the sender and not the receiver. So whenever you do a set and get operation, both localities have to call the appropriate functions. So one has to call set, the other one has to call get. But the side arguments have to refer to the other one. So the sender has to specify the receiver ID, and the receiver has to specify the sender ID in order for the communication to work properly. Again, there is an asynchronous version, which just, instead of giving you the actual T it received, it will give you a future to that received value. And you can wait on it, or can attach continuations, or do whatever you want with it. Again, the receiver is implicit too, because it's a site that, or the locality that calls get is the implicit receiver. In order for data item to be delivered, both the sender and the receiver have to agree on a must call set and get. So one has to call set, the other one has to call get. Otherwise, no communication happens, obviously. And the tag has to be matching between the two. And the sender and receiver localities have to be matched as well. In other words, the sender has to specify the receiver, and the receiver has to specify the sender, and then you can communicate between the two. The data type passed to set must match the data type explicitly specified on the receiving end. As I said, we have to have a means of finding out what is that byte stream we receive, what does it represent? And the only way for the system to know what the byte stream actually represents is to tell get, please expect a t, expect an integer, expect a double, expect a vector of doubles, or whatever. Otherwise, the bit stream can't be properly interpreted on the receiving end. So the receiver must know what type of the variable the sender used to generate the byte stream. So as I said, both are asynchronous by default. Set returns a future that becomes ready once the message was accepted, and get returns a future that holds the received value that becomes ready once the value has been received. The synchronous versions, you just pass launch sync as a first argument, and you get synchronous versions of the two. Okay, let's look at a ping-pong example. Let's send things back and forth. Have two localities, one locality sends it to the other one, and the other one sends it back to the first one, just to create an example of that. How do we do that? Well, again, think about it as a distributed application where the process runs on both localities. We run it on two localities. Both ask the system for the world channel communicator. Then we set the value, send it to the other locality. So let's assume this is locality 0. We send it to locality 1. We send the integer we initialized over and use some tag. And then we call get. Note, we have to explicitly tell it what type to expect. And say, OK, receive it from locality 0. Then we do the opposite. We say set. Now this time, send it back to locality 0. And the get operation receives it from locality 1. And then we print the value. Now the question for you, one of those stupid questions where you have to answer no just to give you a hint, will it work? Now you tell me why it doesn't work. Why doesn't it work? If I run that, I get this. I get received 42 and then sing sang, and nothing happens. So one of the processes is able to do it, and the other process is not able to do it. It's hanging, it's waiting. So if you look at the code again, it's actually easy to understand. Remember, this code is run by both localities. So on locality 0, this set will succeed, everything is okay. It will send the value over, and then it will wait for the value to come back from the other side. But locality 0 will wait for locality 0 to receive a value, which will never happen, because locality 0 is never sending anything to itself. So it will sit here and will never finish. Whereas the other locality will succeed. It will send some value to itself, which is okay, no harm done, but it will not do anything useful. And then it will wait for locality 0 to send its value over, which locality 0 did. And then it will send it back to the other locality and will successfully print things. So this will work. But how can we make it work in the context of that many processes run at the same time? How do we do that? Any suggestions? How would you do it? How would you do ping-pong under these constraints we are living in? So we can't write code this way. What can we do? Anybody? Well, it's easy. Well, this is the analysis I just did verbally, essentially explains why things don't work. But how can we do it? Well, on locality 0, we do one thing, and locality 1, we do another thing. On locality 0, we just send the value over and wait for the value to come back. And on locality 1, we wait for the value to come in and send it back. And this time it will work. Please note that I'm using the same locality for the send and the receive operation for both localities, because locality 0 communicates only with the other one, sends it first and then receives it. And this locality will first try to receive it and then send it back to the same locality. And this will work. So in this case, we will get the result on both localities, and things will just do the right thing. So only process 0 sends this, only process 1 receives it here, only process 1 sends it back, only process 0 receives it, which will do this. Okay? It will probably print it twice. This one is printing it not at all. Okay, it prints it only once because the print statement is only there for locality 0. Here as well. So yeah, it will print it once and will exit successfully. Everything is okay. So be careful with these things, and always remember that you're working in the context of several localities working at the same time. So the code is the same for all of them. So you have to be very careful what you actually do on which of the localities, and what will succeed and what might hang, because you're waiting for things that will never happen. By the way, if I run the same code on 8 localities, it will still work, because the other localities will not do anything, right? Remember, if locality is 0, do this. If locality is 1, is that. But if locality is 7, the code will not do anything. It will just exit. So this, in this case, should be fine as well. Any questions about that so far? No? Good. Then let's kind of sum it up and say we need 4 functions for an HPX in order to do point-to-point communication. We need getWorldChannel communicator, we need getInfo on that communicator, and we need get and set. 4 functions. That's all you need to know in order to communicate between processes in a point-to-point way. Straightforward, very simple to remember. Just 4 functions. What are the other 4 functions in HPX I mentioned? Those are related to communication, to collective operations. Well, we have seen the code before. We have getWorldCommunicator, we get the info, we do broadcast, and we do reduce. So again, 4 functions you need to do to orchestrate distributed computation of arbitrary computations you want to do, as long as you're able to fit it into that scheme. Again, just 4 functions you have to remember. That's it. Should be easy enough to do that, right? Any questions? Well, just to remind you, get the locality IDs, send it over, do your computation, receive the results. Very same scheme as before. It's just the same slide, essentially, we had before. So these 2 programs give you the ubiquitous pattern you need to do distributed computation. You need to have means to send things over to another locality in a peer-to-peer fashion. Sometimes you just want to send a single value to another locality so that the other locality can do things. Or you can use reduction operation or broadcast operation, or there are other collective operations we will talk about next time that allow you to orchestrate communication on the whole set, on all localities, because all of them need to contribute or need to participate in a particular operation. Just to sum up, to give you a kind of pictorial representation of what broadcast actually is, you can think of a set of localities which have a set of variables. In this case, it's variable A. And after the broadcast operation, all of them have A. So it's a simple way to understand that. And the broadcast takes the communicator and the value, and the rest you can just take as it is. You don't have to specify that. So the value is the send buffer for the locality 0, but is the receive buffer for all the others. Right? It's a reference. So on locality 0, broadcast will actually take the value, and on all other localities, the receiver will put the value into that variable, into that argument. So all localities connected or that are part of the communicator must call that function. Otherwise, it will not work. Otherwise, none of the localities will finish the operation. just a bit more information about it. I'm not going to read it to you. It's just an explanation of what the arguments are. Please note that this function is one of the communication functions that are synchronous by default. There are asynchronous versions for broadcast, but here you need two different broadcast functions. A broadcast to, which is the one that sends the values, and a broadcast from, which has to be called on the localities that are expecting to receive a value. But that is just for design reasons. If you use it in a synchronous way, it's a straightforward same function you can call everywhere. Yeah, just the list, what's the API of these broadcast to and broadcast from. And the thing to note is that both return a future. So they are asynchronous by design, which again allow you to overlap that broadcast operation with local computation. So you can do other things while that broadcast operation is happening, and then synchronize with the result later on. The other one we talked about was reduce. And here we have the other scheme. Each of the connected localities has a different value of that we want to reduce. And the reduction operation will make locality 0 receive the sum of all of them. So exactly what we talked about, right? We have 4 localities, each of them has its own value, and after the operation, locality 0 has the sum of them collected and returned to it. And again, reduce here is a synchronous by default, and that result is used as the value to send, and on locality 0, it's also used as a value that is being received. So the value is a send buffer for all of them, but it's a send and receive buffer for locality 0. And after the reduce returns, locality 0 will have the reduction result of the values supplied by all the localities. Argument description, I'm not going into that. You can go back to it if you need it at some point. You need more information. But by the way, all of that is exhaustively described in the HPX documentation. So you can go always online and find all of that information there. Again, there are asynchronous versions of reduce, just for your information. They are split again into 2 functions, very similar to broadcast. One is called reduce here, which is the receiving end, and reduce there will deliver or provide the values for it. Okay, so what's the conclusion so far from today? Drop D, which is that abbreviation for distributed replicated processes with distributed data, requires data decomposition and communication. So I think we discussed that, well, we almost have beaten that horse to death now. So I think that is clear. So you make data small enough, or the partitions of the data small enough so that they fit into the memory of a single node. That's the whole purpose of it. That model can be easily implemented with 4 functions in HPX, as I showed. You can use a peer-to-peer communication, you can use the collective operations, depending on what you want to do. These processes operate purely locally. Again, purely locally. Every process looks at its own memory, only at its own memory networking interface, but it creates the illusion that everybody works with the same value. It creates the illusion of a single address space that they can work with arbitrary variables that are somehow magically shared between the localities. But always keep in mind that this illusion is only a read-only illusion, because these things represent copies of the things that have been distributed. So when you change one of those instances on one of the localities, the others don't change. So you have to do another communication operation if you want to distribute new values across the system. So when we run a parallel program, we aren't running a parallel program, even if you're running a parallel program. As confusing that might sound, what I mean by that is a parallel program is a Linux process or a executable that is launched in parallel on several localities, on several nodes at the same time. They communicate with each other, they know about each other, and each of those processes works completely locally only and communicates over the network with its other localities, with its other instances of that same process across the system. And all copies execute the same code. You launch the same executable on all Linux processes. All the processes are created from the same code, from the same executable that is compiled once and sits somewhere in the file system. So there's no difference between the different localities. Okay, at that point I'll let you go. Thank you so much. If there aren't any questions, then have a nice weekend, and I'll see you next Tuesday when I will continue with the Laplacian application, and we will see how we can apply all of that to something real and not just computing pi, which is not so interesting. Okay, thank you.